Hello and welcome. All those who are glad this is the last section of Chapter 11, raise your hands. Now, all those who believe in telekinesis, raise my hand. Whoa, good job. In this video, we're going to learn about Taylor polynomials, which are a way to approximate Taylor series. Let's hit the notes. If you take the first so many terms of a Taylor series, you get what's called a Taylor polynomial. The nth degree Taylor polynomial would look something like this. It's just the first so many terms until you get to the one that has x to the n. Now this one would be the nth degree Taylor polynomial with a center of a, where a can be anything. If you could have a equals 0, for example, or a equals 1, or so on. The representation we can use would be t sub n. This would be the nth degree Taylor polynomial. So that represents the nth degree Taylor polynomial. And so an example would be, here's e to the x, which is, as a Taylor series, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And this is an infinite polynomial. But if we stop at some point, then it becomes a Taylor polynomial. If we stop adding and we don't add the infinite number of terms that come after, then it becomes a Taylor polynomial. So the first degree Taylor polynomial for e to the x would just be out to the x term, x to the first term. So that would be 1 plus x over 1 factorial, or you can just write 1 plus x if you wanted to. The third degree Taylor polynomial, that would be 1 plus x squared over 2 factorial plus x to the third over 3 factorial. So it's not too bad. Now, if you went to graph some of those Taylor polynomials along with the e to the x function, so e to the x is drawn in blue in figure 1, and then t1, which is the first Terminator movie, no, it's the first degree Taylor polynomial. That's going to be this line right here, 1 plus x. You can see that it has a y-intercept of 1 and has a slope of 1. T2 would be this parabola here, this magenta looking parabola. T3 is this curve, kind of a light bluish curve. And that's the cubic that we just wrote out here. This is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. One thing to notice is that these Taylor polynomials, the higher degree you go, the better the approximation tends to get. And the approximations for each of these are good around the center. So here the center of our expansion was 0. Our center was 0. And so when you look at the Taylor polynomials, they're going to be pretty good approximations for the function that you're looking at, so of e to the x in this case, as long as you stay close to the center, so close to x equals 0. So close to x equals 0, t1 is a pretty good approximation for e to the x. t2 is an even better approximation. If you were to stray farther from x equals 0, it would stay a good approximation even if you traveled a little bit farther from x equals 0. And t3, even better. You can see that it's mapping even closer to the e to the x function. Now, of course, in the end, any polynomial is not going to win out over an exponential. But as you keep adding the degrees of these polynomials, it's going to more and more closely match the e to the x curve. Now, what's going to happen over on the left side here is that it'll kind of fishtail back and forth. The odd degree Taylor polynomials are going to go down to negative infinity as x goes to negative infinity. And then the even ones will go up to positive infinity as x goes to negative infinity. So it's going to kind of fishtail, but it's going to get closer and closer to e to the x even in that direction as well. You can see the t to the 3, t sub 3, the third degree Taylor polynomial, is really matching closely until you get to about like -1, and then it starts veering off. But t4 would be even better. A little side note is, note that t1 is at x equals 0 is the same thing as the tangent line at x equals 0. So it's the same as the linearization that we learn about in Math 180. So L of x equals f of a plus f prime of a times x minus a. If you plug in a equals 0, you get just t1. You get basically just what t1 is. So that's going to be the same thing as the linearization. It's just a tangent line to the curve at that point. T2 would be a polynomial approximation, and T3 a cubic approximation. So this is a way of generalizing that linearization idea for approximating the values of a function. Now instead of being constrained to just having a linear function to approximate our curve like we did in Math 180, now we can go into higher degrees if we wanted to. Still polynomials, but higher degree polynomials that would match your curve even better. Let's take a look at example 1 where we're asked to find the Taylor polynomial T3 for a function x cubed at a center of a equals 8. All right, well, let's go ahead and look at what we need. Well, looks like we need for T3, we need to get the first derivative, second derivative, and third derivative. We need to go out to the third derivative in order to get out to that third degree term. So let's start taking derivatives of the cube root of x. Well, what I'm going to do is write first the cube root of x is like x to the 1/3, and we'll keep taking derivatives. 1/3. I'm going to write them out in a simplified form so we can have enough room. So this is 1/3, so that's 1/3, and then when you subtract 1 from the exponent, you'll get negative 2/3, which can come to the bottom as a 2/3. Now this is really x to the negative 2/3, so that negative 2/3 when you multiply it in front gives you negative 2/9. But then the negative 2/3 minus 1 gives you negative 5/3, which is a 5/3 exponent on the bottom. The third derivative, you multiply the negative 5/3 and you get 10 over 27, x to the 8/3. Okay, now our center is a equals 0, so we're going to plug, a equals 8. So we're going to plug 8 into all of those derivatives. Let me just go to a different color. And you know what? As long as we're at it, let's go ahead and put in the factorials. We'll put in the factorials as well. So for the first one, though, it's just f of 8, which is 8 to the 1/3, the cube root of 8, which is 2. Okay, so then the next one is going to be f prime of 8 over 1 factorial. That'll be the coefficient in front of the x term, or x minus 8 term, I guess you could say. So this is going to be an 8 plugged in. Well, that the cube root of 8 we just said was 2. That squared gives you 4. 4 times 3 is 12. So this will give you 1/12. Now we're going to get second derivative at 8 over 2 factorial. Okay. Well, here we would have the cube root of 8 is 2. 2 raised to the 5th power is 32. 32 times 9 will give you 288. That one divided by 2 will give you 144. And this is going to be negative. So negative 1 over, oh, but then we have this times 2 factorial. So 144 times 2 will give you 288 again. Okay, so when you work all the details out, you get negative 1 over 288. And then for the third derivative at 8 over 3 factorial, I'm not even going to pretend. I'm going to just write out this is 5 over 20,736. Yes, I was looking at my notes for that one. So you just calculate it out, and that's what you get. All right. So those are going to be the coefficients. So our third degree Taylor polynomial, T3, will look like this. That first coefficient of 2, that's going to be the constant term. Then we're going to have plus, and then 1/12 is our next coefficient, x minus our center. So remember that it's not just x, it's x minus a. It's x minus your center for a Taylor polynomial centered at a equals 8. It'll be x minus 8. Then we have the next coefficient is negative, so we're going to put minus 1 over 288 x minus 8 squared, and then plus 5 over 20,736 times x minus 8 cubed. And here's where it's different from a Taylor series expansion. I'm not going to put plus dot 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 because this is the third degree Taylor polynomial, which ends at x to the third. This is really, it's x minus 8 to the third, but really this is where the x to the third term is going to come from. So that's it. There's the third degree Taylor polynomial. That would be a cubic that would approximate the cube root of x function, at least centered at x equals 8, or a equals 8. So if you look at the figure 2, you have the cube root of x, and here at x equals 8 is where the cube root of x and this third degree Taylor polynomial are going to touch. And that's because we're making this third degree Taylor polynomial centered at a equals 8. If we had centered it at a equals 0, well, then we would be touching right here. Although, actually, that wouldn't really even be possible because then you'd have a vertical tangent line. The derivative would be undefined at 0. So you couldn't really make it there. But you can make the Taylor polynomial like touch at any place along the curve, as long as your derivatives are defined there. So it's kind of like a cubic. It's like a tangent cubic in a sense. It's like it's not, instead of a tangent line, it's like a tangent cubic. It's a cubic that's really close to that function, that cube root of x function, at the point of tangency, which is 8 in this case. Okay, so there's what a Taylor polynomial would look like for example 1. Thanks so much for watching. See you next time.